Welcome to this AP guided practice on compounds and formulas. We're going to take a look at a variety of different ways that we can do calculations for different types of compounds and determine formulas. So in the first one, we're asked what the percent composition of carbon, hydrogen, and oxygen is in ethanol. So we need to start off with our molar mass for ethanol first. And in order to do that, we're just going to add each one of these up. So 2 times carbon. It's actually going to be 6 times hydrogen because we have 5 hydrogens in the first one, and then we have the hydroxyl group, the OH on the end, so that gives us another hydrogen, and then 1 oxygen. So when I went ahead and added that up, my molar mass was 46.068. I'm just going to keep all those numbers on this one. Grams per mole. Okay, so what we want to do is we want to take the mass of each element in the compound and we want to divide it by that molar mass. And so we'll do that for each one of these. So for carbon, we're going to take 2 times 12.01 grams because we have 2 of them here in the prompt. And then we're going to divide that by the molar mass of 46.068 grams per mole, and then we're going to multiply by 100. Okay. And that gets us into a percent. So we go ahead and plug those numbers into our calculator. So 2 times 12.01 divided by 46.068. A lot of times I round to the whole number, and that should be sufficient as well for most of the calculations that we're doing in class. We do the same thing for each of the additional elements. So remember that we have 5 plus another one of those hydrogens. So for hydrogen, it's going to be 6 total hydrogens times 1.008, which is the molar mass on the periodic table for hydrogen. And then we're going to divide that by the 46.068. Multiply that by 100 to get our percent. So 13.13% is what I calculated. And finally, the same thing for oxygen. We only have 1 oxygen. So we're going to take the 1 oxygen that we have, so 16 grams on the periodic table. We're going to divide that by the 46.068. Multiply by 100. And we get 34.73%. So just determining percent composition, it's always the amount of the part divided by the amount of the whole. All right, let's take a look at how to determine empirical formula. So in this next one, we're going to look for empirical formula. And we're given masses. And so what we want to do is we want to go ahead and go into moles. In order to determine any sort of formula, we want to get into moles first. And so the first thing that I'm going to do is I'm going to, for each one of these, take the mass and divide it by that's given and divide it by the molar mass. So for nitrogen, that's the molar mass. We want to start with the 22.40 grams. And then I'm going to divide that by our 14.01 grams per mole, the molar mass from the periodic table for nitrogen. And we're going to essentially cancel out grams and be left with 1 over moles, which is the same thing as moles when we do our units. And we get 1.599. I'm going to write moles. Be very careful that you don't round too eagerly with these types of problems. It's really helpful if we maintain quite a few numbers, at least 3 if not 4 past of those digits past the decimal. If they're whole numbers or larger numbers like these, smaller numbers, again, we want probably at least 4 sig figs to be able to keep from having more major rounding issues. Okay, we do that for hydrogen. So 3.22 grams divided by 1.008 grams per mole. Get 3.194, and so on and so forth. So carbon, 9.60 grams 0.01 grams per mole. And we get 0.08. Again, these are moles. A lot of times I'll drop the units when I'm doing these sorts of problems, but I think it's a really good habit to kind of keep that on the first couple, just to make sure we understand the whole process. And then oxygen. Okay. All right, so once we've done that, we've gotten everything into moles. Once we get into moles, then we can compare the moles by finding the ratio of moles to one another. And in order to do that, what we're going to do is we're going to divide. So the green that I'm doing here is dividing by the smallest number or value of moles. So when we look and compare these, we see that 0.08 is for carbon and oxygen, but that's the smallest value. So we're going to divide all of these by 0.08. And again, that's moles, so we're going to cancel moles. We're really just getting the ratio of elements to one another in this compound. So of course the bottom two are both going to be 1, and then the other two we're going to have 4 for hydrogen and 2 for nitrogen. And so this tells us all of our values, they're whole numbers, so we can stop there, and our empirical formula is going to be N2H4CO, and we're just going to leave it at that in the order that it was presented in. So that is our empirical formula. Now, sometimes we're given data values that are given to us in percent instead of moles. And in order to be able to do this, we're going to make an assumption. So we're going to assume a 100-gram sample. And if that's the case, then those percentages actually would be considered to be grams. And so we're going to go ahead and just change the percent symbol to grams. Okay, you don't need to do any sort of math. We're just going to make this grams for each one of these. Now, the process for solving this problem becomes the same as the previous problem. So let's go ahead and do the same thing again. So we're going to do this for carbon, hydrogen, and oxygen. So carbon, 48.64 divided by 12.01. Hydrogen, 8.26 divided by 1.008. I'm not carrying over all of those symbols this time. I'm kind of doing the expedited version, which is what I normally do for myself. 43.20 divided by 16.00. Okay. So I go ahead and calculate each one of these. I've already done that ahead of time, and I get 4.050 for the top. For carbon, for hydrogen, I get 8.194, and then for oxygen, I get 2.7. Again, we're going to divide by the smallest number, which is 2.7, so let's go ahead and do that. 2.7, we know that's going to be 1. This one comes out to 3. And the last one comes out to 1.5. Now the challenge is we cannot have a decimal, and we can't just round, okay? So I'm going to give you a little rounding suggestion or rule here. If not a whole number for those ratios, okay? If we don't have whole numbers for each one of them, or if it's not 0.1 away from the whole number. Excuse me. If it's 0.1 away, we can go ahead and round. Okay, but if it's not, we have to multiply. So must multiply by a factor to get whole numbers. Now, this is a bit tricky because what are you going to multiply it by? I think with the 0.5, it's pretty intuitive. So if we have 0.5, so 0.5 is equivalent to 1/2. So we're going to multiply by 2 in order to be able to get a whole number, right? So that's kind of just a little theory behind that. There's some other tricks to that. If it's not 0.5, what do we have to multiply to get to the whole number? So in this case, we're going to multiply each one of these by 2. So each one we have to multiply by 2. So it's going to give us 3 for carbon, but we have to do this to all of them. 6 for hydrogen, and then 2 for oxygen. And so now our empirical formula is going to be C3H6O2. All right. We have 2 more problems. I know there's quite a few on here, but I just wanted to make sure we worked all the different directions possible with these types of problems. So in the next one, we are asked for the molecular formula. Okay, so I'm going to go ahead and highlight that. Molecular formula, not empirical formula. And we're given a molar mass in order to do that. Now, the interesting thing with this is we're going to solve just like we have for empirical formula first. Okay, so I'm going to write that little designation. So if you're not given the empirical formula, we have to solve for it. So solve for empirical formula. First, if not given, okay? So we're going to do the same thing we've done on the other problems. So now we have P, 26.7 on the periodic table. Phosphorus should be 30.97. And that gives us 0.862. Nitrogen is 12.1%. So we're going to make that into grams, and we're going to divide that by 14.01, the molar mass of nitrogen. And I got 0.864. That should be really 1-to-1 ratio on those two. And then finally for chlorine, I have 61.2 in the prompt for the data point and 35.45 grams per moles on the periodic table. So this one we end up with 1.73. Again, we're going to divide by the smallest number, which is 0.862. And we get 1 to 1 to 2 of phosphorus to nitrogen to chlorine. So now we have an empirical formula that is going to be, I'm going to round that as EF for empirical formula. It's going to be PnCl2. I want to find the mass for this. So just like we find molar mass, we add up the mass of nitrogen plus phosphorus plus 2 times the mass of chlorine. And I found that that was 116 grams per mole. I probably rounded that when I did it. Okay. Now, in order to determine what the molecular formula is, it's going to be either it's some factor, either the same or some factor of that empirical formula. So what we do is we take the molar mass, the 580 grams, 580, and we're going to divide that by the 116. Okay. And when we do that, I get a factor of 5, which means the empirical formula mass is, or the molar mass is 5 times greater than the empirical formula. So we multiply the empirical formula by 5. So we're going to do 5 times PnCl2, and we're going to make this into subscripts, right, down below. So that's how we write formulas. And we end up with P5N5Cl10. And that is our molecular formula. All right, the last problem is actually what we would consider to be an analysis, a combustion analysis question. And so there's a few different steps to do with this, and so we're going to take a look at the process for doing this. We are going to first start off with our mass of our sample of sugar. It's composed of carbon, hydrogen, and oxygen. Okay, and we're given some information. So we know in a combustion reaction, we always have some sort of hydrocarbon. So for combustion, we have some sort of hydrocarbon plus oxygen that produces CO2 and H2O. And what we can do is we can evaluate the carbon dioxide to determine the amount of carbon. And we can evaluate the amount of water produced in order to determine the hydrogens. And then we have another little trick that we're going to use to find out the oxygens in this case. So I'm going to start off with my moles. I want to know moles and mass of carbon. Okay, so I'm going to do moles of carbon, and then I'm going to add the mass onto the end. I think that's the easiest way to do this. So I'm going to try to streamline the process here. So we're going to start with our 2.20 grams. Okay, so 2.20 grams of carbon dioxide. We know that carbon dioxide is, and I'm just going to round these to whole numbers for my molar mass, 44 grams of CO2 for every 1 mole of CO2. Now, for every 1 mole of CO2, there's the standard that we know that there's 1 mole of carbon, right? Because for every molecule of CO2, we only have 1 carbon. And so we can determine what the number of moles are, and I got 0.05 moles of carbon. So that's the first part of that. And remember, I said we're going to do mass as well. So what we want to do is go ahead, and I want to subtotal that because I need to have the mole value to do some other stuff. So now we're going to take 1 mole of carbon, and we're going to use the molar mass of 12.01 grams per mole for carbon to find out that there were 0.6 grams of carbon. All right, we do the same thing for hydrogen. So now let's do hydrogen. So we're going to do moles of hydrogen, and we'll do mass of hydrogen. So, and mass of hydrogen. So I'm just color coding those different process steps. We want to do both in this case. All right, let's start off with our 0.900 grams of H2O given in the prompt. It's 18 grams of water for every mole, so that's our molar mass. For every 1 mole of water, there are 2 hydrogens in a molecule or a mole of water. So we want to do 2 moles of H. All right, so that gives us 0.1 moles of hydrogen. Okay. And then we're going to convert into molar mass, and you'll see some kind of things that you might be able to streamline with this. So for every 1 mole of hydrogen, it's 1 gram essentially. And so we get 0.1 gram of hydrogen. Okay. Once we get to this point, we know the moles of hydrogen and carbon, which we can use to find empirical formula, but we do not know the moles of oxygen. So to find the mole of oxygen, we know that conservation of mass or conservation of matter says that the amount of our sample that we start with should be the mass of the total of carbons, hydrogens, and oxygens at the end. And so what I want to do is I want to go ahead and add those values up. Okay, so I am going to grab this color here, orange. I'm going to add these two values up for mass. And so that's going to give me the mass of carbon plus hydrogen, and I get 0.700 grams or 70 grams. Okay. I'm not too worried about sig figs in these problems. We're just keeping those numbers with us. So finally, let's go ahead and take a look at what the mass, we just calculated the mass of hydrogen and carbon. So we're going to do the mass of oxygen first, and then we'll go ahead and do the moles of oxygen. Sis, I'm finishing the video. I need you to step out for just a minute. Thank you. Thank you. I'll be out in just a minute. Sorry about that. Got the kids going on here. So we're going to take the 1.5 gram sample that we started with here. So 1.50 gram. We're going to subtract from that the 0.70 grams from carbon and hydrogen to find out how much of it was from oxygen. And we get 0.80 grams of oxygen. Okay, and then we're going to go ahead and just convert that into moles. So we know that there's 16 grams for every 1 mole of oxygen. Life's a little tough at the Moser house tonight. And we get 0.050 moles, okay, of oxygen. Okay, now I have moles of each. So the reason I had to go to grams for carbon and hydrogen is based on the fact that I needed to find that missing piece for oxygen. Sometimes that could be nitrogen. If you just have a hydrocarbon that's carbons and hydrogens, you don't have to do that extra stuff of going to mass. So just kind of keep that in mind. There's a couple different problems that you might see. So now the final step for us is we want to go ahead and figure out the empirical formula. Just like we have with all of the previous problems. So for carbon, it's going to be 0.05 moles, and we know that that is actually the smallest number of moles, so we're going to divide by that, and we find it's a ratio of 1. For hydrogen, it's 0.1 divided by 0.05, and we find that that is a 2. And for oxygen, it was also 0.05. So that means we are going to have a ratio of 1 on that as well. And so now our empirical formula we can write as CH2O. All right, I hope that is helpful for you, and we will take a look at some additional practice problems.